All right. Good morning, everybody. Just waiting a couple of minutes. Let a few more people filter in. All right. A little bit bright. Okay. I got Naveen. What's up? Yeah. Previous lecture videos to view. Yes. If you first of all, everybody can hear me, right? Okay. Good. Yeah, previous lecture videos, they're out there on Slack, in the Slack channel, ML lectures, ML lectures, and then go to the pinned, to what's pinned there, and you'll be able to see it's all on the DSDJ repository. So yeah, if you ask the same question on Slack, I can point you there. I know if you've got this question, everybody else does. So, all right, very cool. Okay, so let's get started. Today's talk on neural networks. This is one of my favorite subjects, neural networks. You know, it's kind of the building blocks for deep learning. It's a departure from statistical methods, and to me, it's just extremely fascinating. So, good morning, everybody. Asta, you're just talking to the panelists. Sunil, you want to switch it to all panelists and attendees. Evangelos, yeah, Zoom defaults to just talking to the panelists when you sign in, so you have to switch that. Okay. This is a community here, Slack, you know, got the whole Slack channel. So I want everybody to be talking to everybody, not just me. All right. So what we're going to talk about today We'll start with the introduction to the neural network structure. And basically a simple neuron, and then expand that to a network, and then I'll show you how that becomes a deep neural network. It's not really that different to be a deep neural network. So I want to dispel the myths about deep learning. Hopefully, by the time you're done with this lecture, you'll have a basic understanding of how neural networks work, how actually deep neural networks work, because what we're going to cover today is the simplest deep neural network, which is not much more complicated than a simple neural network, and you'll see what I mean by that. We're going to apply that deep neural network to an XOR the XOR data set, this is kind of like the hello world of neural networks, is applying it to the XOR database. The XOR, which you guys are familiar with, the XOR function in logic. But if you're not, you'll see it here. So, and then we're going to expand that to another somewhat hello world neural network application, the Iris dataset. That's what's after that. And then we'll talk about the homework, and also the quiz 3, which I didn't put the answers here. I just showed it again because I haven't, gotten enough responses yet for me to show the answers. I know everybody is behind in my class, and I can understand that. This is somewhat of a fire hose of information to everybody. It's a very broad field, data science, machine learning, and in 9 weeks, I'm trying to cover everything at a pretty high level, very fast, and I want everybody not to become experts in the field of data science and machine learning, but more of, I want you to be exposed to it, to all these things through my class. Now, to become an expert, that's more up to you. Everybody is a key to getting a job in this area is not knowing everything in data science. I want to stress that. The key is to be broad in your understanding, your common sense about all of the topics in data science, and you one area or two you become really interested in. You delve into it and become very, very good at that area. That's what people want to see. They don't want to see that you're an expert at everything. There's just very few people that are like that, if anybody is. So that's not what employees are looking for. They're looking for your ability to learn, your ability, your excitement about this subject. So I'm going to give people more of a chance to finish this quiz, but you're going to have 2 quizzes to do, quiz 3 and quiz 4. But this shouldn't take you a lot of time. And also, I don't know if you noticed, but I just use any means possible to come up with these answers. I know initially I said don't use Google, but At this point, I'm making the quizzes, a little bit harder to find through Google. So Google's fine. You guys are doing great on the quizzes, by the way. I haven't published the results yet, but very happy. So here's the quiz. It's over last week. I'll do a little bit of review. Can't do too much because we have a lot to cover. So most correct order for EDA in the machine learning pipeline. I listed a lot of steps here. Okay, which one is the best order? There isn't necessarily the one that says what's the correct order. It's the most correct. Okay, which of the following is not a data format? Should be able to pick that out pretty quickly. All right, so CSV can be described as which of the following exactly. So my wording on that one is very interesting. Which of the following would not be a reason for applying transformation to your feature? I'm being very tricky in some of these. Which of the following data cleansing processes has the potential for losing the most information in the model? That one should be pretty easy. Which of the following is not true about correlation matrices? Which of the following is the simplest feature engineering method? So yeah, I wish I could go more into this. Okay, a lot of people are just talking to the panelists, so you're not talking to the group. You need to switch your the setting there from change it to all panelists and attendees. Okay, so I talked, this is a little departure, this is I'm still kind of in an introduction here. Motivation for this field, what is your motivation? I'm showing a couple things here, and part of the homework for this week is for you to tell me what your motivation is. And it's not to get a job in this area. It's why do you want to learn this? And this goes back to, okay, you don't need to become an expert at everything. That should not be your motivation. You should become an expert at like one area and broad at everything. So what part of data science do you get excited about? This is part of my motivation here. This chart of showing the growth of Python. The other languages are not going down. Java, JavaScript. Python is just getting more popular. PHP may be the only one that's dropping right now, but Python, which people are using it for dealing with big data, a lot of data. It's just such a nice language to work with, I think, compared to other ones. I've had this theoretical conversation with a lot of people. But yeah, just something like this gets me excited about learning, because Python is the language of data science. R is also, but it's not as much as Python. It's more of the legacy of data science, the statistical end of it, which is very, very important. Don't get me wrong. Also this guy, okay, he has, if you get a chance, go out there and look at his stuff. If you want to get excited about deep learning, about what it can do, just take a look at some of his demos, some of his videos, and then for everything, almost everything, if not everything, I haven't checked, but he's got the GitHub, he's got the programs, so you can just go run it yourself. You know, the code maybe is complicated, but you can run it. And if you can run it, you can dig in. You know, you can study each line, and end up, you know, understanding it, because code is a language. So it's the language of just read it, and then you can understand it. So just showing you some of my motivation. This right here, I know I posted this on Slack, but I'm developing it further. You know, I'd love at some point to see my research pick back up as far as the number of citations per year. But just looking at this and seeing, you know, not only, okay, do we have a exponential decline because the research has been, you know, hasn't been added to. You know, there were 6 papers. But yeah, just seeing the effects of the nuclear winter, you know, from 97 to 2005. And then in 2005, it bottomed out with Hinton's introduction of deep learning. People got interested again in neural networks and their advantages over statistical techniques. My papers were all about that right there, applied to the semiconductor manufacturing area. But you know, then you have this rise in 2008 up to 2008, where in 2008 they coined the data scientist you know, job description, and then it started declining again, which is funny. Once you name it, then you can then it's not as exciting, I guess. And then it picked back up again in like 2012 to 2013, which happens to be around the time that I moved to San Francisco. And I saw all these meetups that just got super popular. Meetups, conferences, you know, and I hit all of them, as many as I could, you know, 2 or 3 a week. So, you know, I was, you know, finally, you know, I was getting back interested in that time, and I just happened to move here at that time. So just some coincidence on my end. But anyway, last year only 4 people mentioned my work. Oh, and by the way, there's, I don't know how many, probably 10 patents in all of this. I thought there was only 1. I did some more research. There's a whole bunch that mentioned my paper, one of my papers. There were 6, so I'm not sure which one it was, but I have to do more research. But anyway, this is how I get excited about this. All right, so what are these neural networks? You know, where do they come from? Oops, what happened? Okay, here we go. Sorry about that. Okay, so back in what, I talked about this back in the early 50s, late 40s. You know, they started to understand, you know, biologically what a neuron was in our brain. And this is a diagram of that they came up with, and they modeled it in mathematics. You know, they took science and physics and chemistry and wrote programs, wrote equations to model that. And this is what they came up with. You have inputs, X, we'll call those X. And they get those inputs get attenuated, get multiplied, get you know, controlled by this synapse. And the synapse basically is the connection. It's these terminals, which in this one I don't show the synapse, but it's these endpoints for the axons. An axon is basically communicating the information out of the last neuron. Okay, output axon. That's this arrow on this end, but it's the same as the input to the next neuron. So it's multiplied. You multiply that. So if your synapse turns off that input, then you won't get anything into the dendrite, into the next neuron, the cell body. The cell body, okay, sums up all of those inputs. Basically, if you have enough signal coming in, then from all of your inputs, then it turns on that neuron. You also have this bias in here, which won't talk about that as far as the physical part of it, but just think of adding up all the inputs, and eventually that neuron gets activated, okay? And that activation function is this F. You know, first you add up everything, and then you pass it through this, quote, activation function, which is the turn on once you reach a certain threshold, okay? So that's how this, how a neuron works from a mathematical perspective in our brain. This is a simplification, somewhat, and there's a lot more information about this out there. My last lecture, when I went through this before, I went through this in a lot more detail. But then, you know, it's like, okay, why, you know, this is biology. Why are we teaching biology in here? But to understand, and my goal is to get people to understand where neural networks come from. People say they're not explainable. You know, it's not, they're so complicated, but it's not. I'm breaking it down to something very simple. And as you build it up, there's a lot of explainability that's there. It's just people don't have a grasp on it yet. It hasn't been distributed, but it's there. Okay, so here's another picture of what we just drew. It's really not much different. I just drew it in a different way. I broke it apart a little more. Yeah, so you have all your inputs, your X, and then one of those is the bias, which basically it makes it so that if all your inputs are 0, if it's off, you still have something going into your summation, because all you're doing is multiplying by these weights. But if you have a zero matrix going in, it doesn't matter what your weights are, you end up with no activation. But you want to be able to have some kind of activation even if all of those are off. So that's why you have this bias in there. And that's another weight. All of these inputs are multiplied by these weights, summed together, and then passed through an activation function. And you know, these W's represent synapses. Okay, so yeah, I got a question. The numbers next to X are indices. Yes, that's a good point. Yeah, in this diagram, it's these are just indices, not power. But going forward, I'm going to write those as substring rather than superstring. Okay, so okay, now that activation function, let's talk about that for a minute. There's several different kinds out there. This is a pretty, I wouldn't say exhaustive, but it's a pretty good list of those activation functions. So here's a plot of what they look like. X, you know, plot X versus Y, input versus output. This is the function. The most common one, well, the introduction one is this binary step. It's basically, it's either off if nothing is activating that neuron, or it's on if you've reached a certain threshold. So it's if X equals f of x equals 0 if you're on this side of the equation, if x is less than 0. F of x equals 1 if you're on this side of the equation. So this is kind of the intro. This identity is an activation function, but there's no point where it turns on. It's just a reflection of what's on the input. And this is where linear regression comes in. It's just basically passing it through. Once you do this, then you get more to the logistic regression. So neural networks are really nothing more than linear or logistic regression. People don't really realize that, but you're stringing those together, and then adding some more features to it. People have added on to neural networks as far as different bells and whistles, you can call it that, like dropout. But it's really nothing more than linear or logistic regression, strung together maybe, when you have more than one layer. But yeah, so there's other functions. This is a very, very popular one. The soft step is what it's called sometimes, but it's the sigmoid. But you can see all of these on the left hand, there's nothing, and on the right hand, it's activated. Now this is the RLU. This is very much more popular today, mainly because it's just such an easy thing to calculate. That's it. But it took over in some applications. The original ones were just this sign sigmoid. So I won't go into all of these. We're just going to take a couple of these as being the kind of the ones that are the most popular, and we're going to work with those. Now, something you need with these equations, with this, and we'll get into this more in a second, is the derivative of these functions. You need the derivative in order to back propagate through your network, in order for the network to learn. You need the derivative of that function, and we'll see why in a minute. In specific, we'll need the partial derivative. But don't get hung up on this calculus. It's very, very, very easy calculus. If we use some more of these more complicated ones, which nobody does, not anymore, then you might need more complicated calculus, but you don't. I'm trying to dispel lots of myths, lots of barriers to using these. I'm just kind of being complete in this lecture. Okay, so okay, got the question. Which activation function is used the most nowadays? There are two that are used the most. There's this one, logistic, or a lot of people call it the sigmoid, or the ReLU. This one, Prelude, this is kind of the newest thing, but not a lot of people use it yet. Why do you need a derivative? I'll get to that in a minute. That's coming up. Okay, so now let's go back to the simple part of this, the structure. Okay. This is the most basic neural network. Okay, it looks like it's a bunch of neurons. Okay, I'm just showing one neuron. Okay, got another question. Okay, Is it required to know all these things about neural networks to become a data scientist? No, no, not at all. It's good to have a good common sense about this, but you don't have to know this in order to become a data scientist. This is one of the specializations that you can go into, but you'll see this many times, and I'm going to put a bunch more articles out there for people, and also if anybody is in this area, post stuff that you've seen, or if you're not in this area and you come across something, post it out there on Slack. This is my passion. Okay, this is where I like to just delve into. But yeah, this is just one tool in your toolkit. All right, so this is one neuron here, where you have a bunch of inputs. And misspelling here. Okay, and this is a more complicated neural network where they've added a hidden layer in the middle. Here's your one original neuron, but then they added another layer. So this is where your neural network, this is a basic neural network, became deep learning. Okay, that's all deep learning means. It means having more than one layer. And it's become this thing where there's 1,000 layers, and that's what not 1,000, 40 or 50 or 100 layers. That's what deep learning has become. But all it means is one more layer, because you can represent more than just a linear problem if you add this layer in the middle. That's the advantage of deep learning over like logistic or linear regression, because that's what you really have if you only have one neuron. Okay. To get context, do we have hidden layers in a biological example that I explained? Okay, yeah, that's a great question. In the one that I showed one neuron with a bunch of inputs, and the output is going to another couple of neurons. But if you just cut that off in the axon, that's your activation, like that's telling your muscle to move, that output. Then you just have one neuron going to an output. If you have the output going into other neurons, like different layers, then you have deep learning. You have multiple layers. Something in between your final output, which is moving your muscle, and your input. Okay, all this is useful if you're getting to deep learning roles. Also, sometimes as a data scientist, you might want to apply deep learning and check if you can get better results, but it's only the case if you have a really huge data set. Okay, now something that I need to stress, okay, I said this a second ago, but I got to stress, one neuron on the output is logistic regression or linear regression, okay, depending on what your function is, your activation function. So the same concepts apply to deep learning that applied to one neuron on the output. It's all the same stuff. It's a neuron. It's a neural network. So yes, it's also useful. What I'm showing here is also useful in linear regression, logistic regression. And I didn't teach those first because I wanted to show that those are nothing more than neural networks. And if you understand neural networks, logistic regression, linear regression are attainable definitely very easily, which we're going into those next week. And those will help with understanding this, neural networks. So deep learning, you just have to kind of have a general understanding of everything, very high level. You don't have to, I mean, I'm going to go into quite a bit of math here, but it's all very simple math. But it's a lot of pieces to it. So it might get overwhelming, but I want have everybody to kind of see it at this level. Okay. All right. So yeah, I'm now going beyond just this. I would say a simple hidden layer. It's simple deep learning to this is more complicated, but it's all the structure's the same. The math is all the same. All I did was multiply up the number of values, the number of weights. But when you use linear algebra, when you create a matrix, then you can do these very simple calculations all with much more easily. You can represent all of these millions of lines in between with just one vector, or I'm sorry, one matrix. But yeah, so when I multiply this up, I can solve a very, very interesting problem, which is image recognition. And some of the first image recognition was done with this, with recognizing handwritten numbers, the MNIST dataset. And you get very good results on something pretty complex, image recognition. I added the number of outputs, which complicates things a little bit. But it's like basically this same problem can be solved with logistic regression, which is nothing more than take this middle layer of neurons out. Then you have logistic regression. Okay, and then, okay, we can go deeper, create deeper neural networks. With this one, we created a wider network. We added the number of inputs to 784, outputs to 10, and they, in this particular example, are 16. But so then here, we added another hidden layer. And this is a 3-layer neural network. It looks like a 4-layer neural network, doesn't it? But one layer is just the input. There's 2 hidden layers, 1 output layer, and 1 input layer. How are the number of neurons decided? That's a very good question. That's a hyperparameter. That's something that can vary and will give you different results depending on how complex your problem is, how many input, how big is your data set, what's in terms of how many rows and how many columns. And the more neurons, the more prone you're going to be to overfitting. So you have to keep that in mind. And in some cases, sometimes you drop those neurons as you train. So that's extremely interesting, the number of neurons. Well, the hyperparameter is the number of neurons. That's the hyperparameter, or the number of layers. Will we discuss toward the end of this class? That's part of the homework. I'll basically just try the same thing we're doing here with a different number of neurons. So in this class, we'll talk about that. Okay, so yeah, extending this to even more hidden layers. This is just a simple one with one or two hidden layers. Okay, how do you decide which neuron to drop if you need to? It depends on whether we're talking about dropout or just reducing the number of neurons. If you're overfitting, then you reduce the number of neurons. That's how you decide. If it's dropout, then your algorithm is deciding which ones to drop automatically. But basically, as the more what they've done with convolutional neural networks is just add a bunch more layers, and they've changed the structure of those layers some, but not much. Okay. If you take out the hidden layer, it's like logistic regression. Before we said if you have one neuron in the output, it's like logistic regression. Okay, logistic regression is no hidden layers, basically. And the number of neurons in the output is that you can do logistic regression if you have multi-output model. So it's just how many layers there are. The number of neurons in the input equals the number of inputs, yes. Well, okay, this input layer, these are not, quote, neurons. It's just the input. Just the fact that I put them as circles here makes them look like neurons. They're not neurons. It's the number of inputs equals the number of inputs, the number of columns in your data set. Okay, so just more complex, deep learning, convolutional neural networks or recurrent neural networks or autoencoders. I'm not going to go into those here. Those are a later class. And again, here's the structure of what those look like. CNNs are these, have a whole bunch of layers, and they change the structure of the neurons a little bit, and the number of connections in between. Let's see. Okay, question. When we say the number of layers, do we count the output layer as well? For each, for example, is this a three-layer network, 2 hidden layers, and 1 output layer? Yes, because the output is a neuron. So yes, it's one of the layers. Good questions. Okay. Okay. So yeah, as far as changing the structure, when you do the RNNs, recurrent neural networks, there you're starting to change the structure some. And then the long short-term memory changes the structure even more of a neuron, but it's adding to it. It's not, CNNs are changing the structure very, very, very little. So it's not, it's not something that you need to worry about learning something completely new in order to do convolutional neural networks. RNNs are more complicated, but yeah. Okay, so that was the introduction to neural networks. And that was half the lecture. This other half is going to be actually coding them. So what we're going to do is look at the XOR data set, very simple data set, and we're going to go talk about the feed forward calculating the output from the input, the math calculations, and then looking at that in Python. And then we're going to do the learning part, the backpropagation, which is where we will use the derivatives. And I'll explain why we use the derivatives. But we're going to do the math. I'm going to show the math calculations and then the Python code to mimic that. And then okay, and I'm going to do a two-layer neural network here. So we have two different calculations we have to do as far as the learning goes. And I'll explain that. And then, and all of this will be developed on using the XOR data set. Then I'm going to extend this to the Iris data set. Okay, and a little bit of review, just showing this slide again. All the inputs, I'm naming X. And in this particular case, I have M inputs. For the XOR, M is going to be 2. We have 2 inputs. XOR problem is X, like A XOR B, which I'll get to that in a second. But we're only going to have 2. And then there's these weights coming in, getting, multiplying by each one of these inputs, including the bias, summing it all together, and then passing it through this activation function. And that's the neuron. So and then the output is we're feeding into the next layer. So just reviewing this for a second. So here is the structure, and here I'm renaming things a bit. The X I'm leaving the same. So X0 is the bias function, or the bias variable. X1 and X2 are our inputs, X1, X2, and Y. This is our data set. Very, very small data set, okay? And it's 1 XOR 1 gives us a 0, 1 XOR 0 gives us a 1, 0 XOR 1 gives us a 1, and 0 XOR 0 gives us a 0. So we're adding one more input, which is that bias, 3 inputs, and then passing to this hidden layer of neurons. And each one of these lines is going to get multiplied by a W as it gets summed, it gets passed and summed into the hidden layer. Then it's going to get passed through a activation function, and then we'll go into your output. We'll feed your output layer, 1 neuron, and that 1 neuron is either going to be a 0 or a 1. That's the output. And then you have those W's in here, multiplying each one of these outputs times another W, and then sum together in your output. So here is, and now we're going to start breaking this down and showing the math. This is, except for, okay, ignore these little arrows and the outside, okay? I'll explain that in a second. This is showing one part of our network. And okay, this is showing this second part where I have these hidden layers and I'm multiplying these by these W's to get my output. These hidden layers have an input, which is, imagine those inputs coming in from 3 places, and it's being summed together and summed and multiplied by those W's. So, so as you can see, this is this feed forward part. Forget these other ones. We'll get to that in a second. The feed forward is nothing more than multiplying and adding. The z's are a weighted sum of the inputs. So we got a z for our hidden layer, we got a z for the output. And then a is basically our activation function of that sum. And we're going to use the sigmoid, that particular one. So that's the feed forward. Now let's talk about the feedback. Okay, we start with the output, and we're going to go right to left here. Before, when we feed forward, we went from left to right. Now we're going to go right to left. So in training, what you do is you say, okay, once I've fed my input forward, how far am I off, right? There's an error. And what kind of error are we looking at here? We're looking at sum squared error, where we have an actual output, y, and then our output of this neuron is the function, f of x. That's what we calculated feeding forward. We subtract those, and that gives us our error for that input. And then we square that, and that gives us, turns any negatives to positives, and then we're dividing it by 2. And that dividing by 2 is just to make things simpler later on. Okay, but basically what this is just a way to say this is the squared error, and just divide that squared error by 2. So that's our error. And what we want to do is minimize that error. We want that error to go away, right? We want to train this network to get that error to be minimal. And how do we do that? What we're going to do is we're going to adjust different parts of this network, things we can control, so that that error goes down, so that it goes away. So what you do is you take the derivative of that error and go in the direction of a negative derivative. In a derivative is, you can picture this, it's the slope of a line, right? That's how graphically it shows the derivative. And there's a nice graph I can show, and I will post it later, of graphically what do I mean by a derivative of a function reducing the error. But what you do is you take the derivative of that error, and you want that to be negative. That means that you're moving toward a lesser error. So, and what we're going to do is do a partial derivative of that error with respect to your weights. And what that means is, how does that error change when a weight changes? And then what we're going to do is try to change that weight so that that error reduces. We're going to adjust the weight. And we do that by moving in the direction of the negative derivative. Okay, that's the math. And you repeat that math over and over again in order to train the neural network. And I'll show it again here. Actually, in a few minutes, I show it again. But okay, so now let's talk about how this looks in Python so far. Okay, because I just talked about all this derivative and stuff. but that's not important until later on. What I just showed you was the kind of a preview of what's important. So don't worry that you didn't get it in a couple slides. We'll do that again. But first let's set up the rest of the problem, which was this, our data set. Now there's some other parameters which we'll get to what they mean in a minute, like ETA or the learning rate. These are other hyperparameters that can be used. And then number of epochs is how many times are we going to train on our data set? This is common in data science. Learning is how many times do you look at your data set in order to iteratively get to your best model. And then the number of hidden neurons is right here. We're going to use 5 hidden neurons. We need NumPy and Matplotlib in order to do this. I'm defining my data set here as an array, as a matrix, and I'm adding a column for that bias. I'm setting it to all ones. But here's my XOR problem: 1, 1, my y is 0, 1, 0, my y is 1, 0, 1, my y is 1, and then 0, 0, my y is 0. So, and in order to make this work really well, what you want to do is randomize the weights. All of these weights is what we're going to learn in order to make this. That's what we have control over changing in this neural network. Those are our degrees of freedom. Everything else in this neural network is just a function, but the weights are a number that's in there. So we're going to set those to random values. And how many do we have? How many weights do we have altogether? Our length of our data set, we have 4. So we have 4 weights going from our 0 to 1, and then how many hidden weights do we have? I mean, how many weights do we have in our second layer? That's the W12. It depends on how many hidden layers we have. I can show you that from the structure. Like if you look at this one. So we have, how many weights do we have all together in here? We have 3 for the input, and the hidden layer is 5. So 3 times 5 is 15. So that's how many weights we have here. And then we have 5 weights here. So I said length of x0. So that gives how many values are in here. It's actually 4 times 3. Actually, I'm sorry. It gives you the 5 times 3. So the length of it is 3 times 5, and that gives you 15. So that's how many weights there are. It's random dot random. Okay, so then we define some functions in here. We're defining a function for calculating the sigmoid, and this function does both calculate the sigmoid and it calculates the derivative of the sigmoid. We didn't talk about that yet, but the derivative of a sigmoid is simply whatever you're passing in times 1 minus that. Okay. Okay, there's a couple questions. Does an epoch signify one pass? Yes. One feed forward, one back propagation to adjust the weights. Yes. Why 5? There's only 4 training rows. This doesn't have to do, we're not talking about the number of rows. This is the number of weights, which is not a function of the number of rows. The number of rows is the number of data sets, the number of examples in your data set, samples or examples. The width of the hidden layer, 5 neurons, right. Number of weights equals number of inputs. It's actually not the number of inputs, sorry. Let's go back. This right here is a random dot random. You end up with your weights being a matrix of values, and the number of values in there, it ends up being 3 times 5. I'm sorry, 3 times your hidden is 5. Okay. Okay, I got some questions also. What does it mean by global minimum? Okay, we'll get to that. And local minimum, okay. Those are good questions. A little advanced for where I'm at the moment. If you post that up on Slack, I can get to that later. But basically, we're trying to just get to a minimum at this point as we train. So the number of epochs will get us toward that, and you'll see that in as we go along here. Okay, so here's the code for training. And we're going to explain where all this comes from, but I'm just showing it all. Okay, so now I'm going to break that code down, and I'm showing you it again here. The first part that I'll explain is the feed forward part, and then calculating the error. So I've got a function here for feeding forward. I'm passing in my input and coming up with an output. So I'm calculating the ZH, which was, if we go back, ZH is here. We're first calculating, the input to this hidden layer. And then passing that through a sigmoid. And then taking that output, the AH, and multiplying it with a dot product times the weights from the hidden layer to the output layer. And that gives us ZO, which if we go back, is here, the input to our output neuron. And then we're passing that through the sigmoid to get our activation for the output, which is our final output. And that's what we're returning. That's our feed forward function. Okay, I got a couple of questions. Okay, number of weights equals number of inputs. How is the number of neurons in the hidden layer determined? Is there a rule of thumb? This comes from experience. Basically, you just try like one number of hits, one number, and then you can vary it. If you vary it, you'll see whether you're overtrained or not. So, and you make your neural network more simple with the smaller number of neurons if you're overtraining. So that's how you come up with it. You get a sense for the number of neurons over time, and a lot of times you're looking at somebody else's implementation of the neural network, and you just take their number of neurons. But what you have to do is you have to, through cross-validation, see how overtrained your network is, and then adjust your parameter. A lot of times you do a grid search. You try a bunch of different numbers and see which one's the best. Okay. All right. So that's the feed forward part. Then you pass that. Well, you use the sigmoid in that feed forward. So that's the sigmoid function. So what you're doing each time in one training pass, which is your epoch, is you're calculating your output using the feed forward, and then you calculate the error of that output, which, like we did before, we took the actual output, we subtract what our predicted output, our feed forward, we square it with the power function, and then we divide it by 2. And these are matrices, and so what we're ending up with is a matrix, not just a number for error. We're ending up with one number for every row of input, and then we add up the error for all of those. So this is the sum of squared errors, SSE. And to put it, to show you the math instead of the Python, so over here, the weighted sum of your inputs times your weights, and that gives you the input to your neuron. And then you pass that input through the sigmoid function, and we label that sigmoid, and that gives you the output, A, or for activation. Should be O, but we use A because we're only in the middle of our network at this point. Eventually, it becomes Y, or your output, but you only your predicted output. Okay, so once you have that hidden layer activation, which I apologize, the AH, it changes to HI in this case. There, you're doing a dot product or multiplication times your next layer of weights, summing it all together. That gives you your Z. We go back to the diagram. That's this Z right here. And then you pass that through the sigmoid again to get your activation on your your final output. Okay, a couple of questions. Okay, why is the output of the feed forward function stored in A? A0 and AH. The function only seems to return one value. Okay, these are matrix. If it's only one neuron, then it happens to be only one value. If it's multiple neurons, like our hidden layer is multiple neurons. Let's go back. It's multiple our hidden layer is multiple neurons. We have multiple A's. But in this, for the output neuron, it's only one A. Okay. So, okay, another. Okay. Okay, so the activation function, I'm just showing it here. It's the sigmoid. It's got a power in there. That's another, I guess, fancy math. So anyway, yeah, here's our error. So that's what's going on in this area. See, the math looks really intimidating, okay? But when you put it in code, to me, this seems like pretty simple, much more straightforward. But you know, it's useful to see where it comes from. Okay, so that's the feed forward. Now, and I would actually jump us into the Python right now and run this, but I created a function. I mean, I created a for loop, and you can't step through the for loop in Python Notebook. You just have to run it. So that's why, you know, I'm again explaining things, you know, by just showing you the code, not actually getting in. We will in a second pull up the notebook and run it. Some of you, I did send out the GitHub beforehand for this, so you should be following along, but we'll actually run it in a second. Okay, so now backpropagation. This is the cool part of neural networks, the backpropagation. This is the learning. So they come up with this learning using the partial derivatives, and they use some simple rules about partial derivatives that once you kind of get the gist of it, it becomes very straightforward. But don't worry so much about it as far as the understanding. I'm going to explain it right here. This chain rule. So I said before that what we need to do is find how to adjust our weights such that the error goes down. So that means, so what does that mean literally? It means the derivative of E with respect to W. If we come up with that and we adjust the weights by that, then we can decrease our error by changing the W. So how do you write that? We write it here as the partial derivative of E with respect to our W's. And W12 means the weights between our first layer of neurons and our second layer of neurons. And those each are W11, 12, 13, 14, 15. So, so in order to, a neat rule about partial derivatives is that if you can come up with the pieces of something that when you multiply it together, you end up with that full partial derivative, then all you need to do is calculate the partial derivatives of each one of those pieces. That's the chain rule. So if we could calculate each one of these pieces, then because when you multiply them all together, you'll notice that the partial A0 will cancel with the partial A0, partial Z0 will cancel with the partial Z0, and you'll end up with partial of E with respect to W, which is what we want. So that's the chain rule. So what we need to do is calculate each one of these. Partial E with respect to A0, partial of A0 with respect to Z0, and partial of Z0 with respect to W. So let's do that. But before we do that, let me show you why I picked that, because that represents all of our pieces, all of our steps that we go through to get from the W to the E. We go from W to Z to A, and then to E. And A, we do some calculation and get E. So each one of these flows a calculation. And I wrote those calculations here, how we get from each step going forward. So if we take the partial of these calculations, the partial of E with respect to A, E is what is the function of E? Since A is F, okay, E equals 1/2 Y minus A. So let's take the derivative of that. The 2 times the 1/2 cancels, and we end up with just Y minus F of X. That's why we picked the sum squared errors. And that's what I showed here. So I simplified this partially with respect to A, and I came up with F of X minus A minus Y. And I could take that and plug it in to the formula, to this chain rule. The second one, which is how does A0, how is it affected by Z0? What's that function? That function is the sigmoid. And that particular sigmoid has a very simple derivative when we take the derivative of it. It's that 1/1 minus e to the z. That's the sigmoid. When we take the derivative of it, we get a times 1 minus a. Let me go back and show you that. Right here, the sigmoid is 1/1 plus e to the minus x. When we take the derivative of it, we get f of x minus 1 minus f of x, which f of x is yeah, it's inside here. But I mean, that's how you do the derivative. Now, notice if we did this simpler one, this binary step, the derivative of that at the 0 is undefined, the slope of that line. So this is a hard one to take the derivative of. That's one of the reasons why people they didn't use the binary step. They found something with a smooth line, so taking the derivative is possible. This has a 1 for the derivative, and then a 0 for the slope, before that. So these can also be used, but this one's a hard one. It has infinite slope here in the middle, so it's a hard one to use. Okay, so just a little bit about why we use that. Okay, so now another derivative that we need to come up with is partial of z with respect to w. So what is the function z? The function z is w1 times AH1 times this output plus w12 times this output plus blah, 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 all of them. It's the weighted sum. Now, when you take a derivative of this with respect to one of these, everything else drops off. And you end up with just one of those. Everything else ends up being 0. So you end up with just the output. So if we take all of these partial derivatives, multiply them together, we end up with our partial with respect to w. And do I actually write that anywhere here? Well, then I show the code, basically, of calculating each one of these, delta with respect to each one of these, and then I just multiply them together, a dot product. Okay, question. Okay, yeah, thank you. So, yeah, that's what this particular code is doing. It's calculating each part of the chain rule and then multiplying it together. And it's the multiplication, since these are matrices, it's dot product. And this one is just a multiplication. So this is how you'd rewrite that that mathematics in code in Python. All right. Okay, another possible question. All right. Okay. All right. So now we need to apply this one more time, because what we've done at this point is in our network. Jump back here. What we've done is we found the partial of all of these with respect to, the partial of the error with respect to all of these weights. So we know how now to adjust these. We move them in the direction of lowering our error. Now we need to figure out how to adjust all of these weights. And now we're moving backwards in our network. We figured out that one, now we need to figure out this one. And this one will depend on what we calculated here for these, but it's the same thing. We're gonna reduce our error. We're gonna figure out what to do with these W's, how to affect these W's in order to reduce our error. And that's what I'm showing here. So what I did was I showed our one output neuron. I showed one of the hidden neurons. There's other ones here. You just have to imagine that they're there. And then I showed the inputs. And just give me a second here. Try this other way. So what we're trying to find is our partial of the error with respect to one of these weights. See, it's a little more farther removed from our output, but we can rewrite it in just a simple chain rule. Partial of E with respect to AH times the partial of AH with respect to Z, and then partial of Z with respect to that weight. So to calculate, now we need to break this down and calculate each one of these. Partial of E with respect to AH, we'll use the chain rule again to find that one. And that one is partial of E with respect to A0. We can write it like this. Partial of A's with respect to Z, partial of Z with respect to A. So basically what we're doing is working backwards, step at a time, to see how this one changes, how we should change this one in order to lower our error. That's how you write this chain rule. And then we have to calculate each one of those, EA with respect to A0, A0 with respect to Z0, and then Z0 with respect to H1. Once you calculate, this is, we've already calculated some of this, okay, from before. It's very similar to this one chain rule. Actually, right here, partial of E with respect to A0. And then there's partial of A0 with respect to Z0. We calculated that before. And then partial of Z0, that's what's different. Partial of Z0 with respect to AH. We need to calculate that one. And that one is the weight. And you just write the Z0 function and then take the derivative of it, and you get the weight. Instead of taking, before we took the derivative of the weight, now we're taking the derivative of AH. With respect to AH, sorry. Okay, so then that's how you calculate this one, and that's W. Now we need to calculate this one, derivative of AH with respect to ZH. Well, that's the derivative of our activation function, which is our output times 1 minus the output. And then we need to find the derivative of ZH with respect to W. And if we write our the formula for ZH, it's the weighted sum of the inputs. We take the derivative of that, we just get our input. So then we just need to multiply those three things together. And that's what we do in our code. We calculate each one of those partial derivatives, multiply them together, and that gives us our output. That gives us our partial with respect to that W, and that's how much we're going to adjust that W. Okay, so a second. Is W the sum of weights that we get from the first partial derivative step? Or is it the weight for a single step? The weights are, it's for a single step. The weights are what we multiply the previous layer by to get to the next layer. Yes, Siddhartha, this can be difficult to understand. Unfortunately, going through it this quickly is difficult. But it's not complicated math. It's just there's so many moving parts that it ends up looking like it's complicated. Yeah, getting the dimensions right. Well, which, how many are we talking about? A matrix, a vector, or a scalar in each one of these? Okay, and we are running out of time. It's probably a good stopping point. I need to continue with this, next week. I think I might move a class in between. We need to talk about this, but anyway, let me just see how much more we got. I compressed this from last time. Okay, yeah, we're getting ready to run the code, so this is probably a good place to stop. I'll review next time a little bit, and then pick up and jump into running the code, next time. Apologize for this ending up being too long, but there's still time to get the previous homework to me and the previous quiz. I don't know how to get people to take the time to do the quiz and the homework. I know this is a lot of stuff, but this is to get to that next level. Okay, it takes a lot of effort and takes a lot of extra time, and that means sometimes it means crunching, other parts, other things that we are doing in our lives. Just kind of going a lot faster, being more prepared. Basically, I want to stop here and pick up next time. So any questions? Let's see. I'll be posting some articles on this, some good visualizations, and ask questions on Slack. I'm not the only one that's an expert on this, so have more people kind of jump on there and to answer questions will be good. But yeah, just picturing all of this. Yeah, that's something we need to do, is get more visualizations. Part of the homework I had from last time is, I'm probably going to put this back on and maybe just show it in class, is really good visualizations for what's going on inside of a neural network. That will definitely help grasp this concept. Picture is worth 1,000 words. So I put a lot of words and a lot of equations here. Next demo, we'll add a bunch of pictures. So let's see, another question. Post this week's homework. Yes, I'm kind of waiting for people to catch up on earlier homeworks, but I will go ahead and post it out there. So, all right, I'll stay on for a little bit longer, but and answer more questions. About another 10 minutes, but